Okay, so I think we are now live once again. Welcome back, everyone, to another edition of Quarantine Thermo. Um, so, really happy that you could join us again. We're still having loads of fun running this thing, so I'm glad that it's kind of still providing some kind of interest and entertainment for the community. We have lots of exciting speakers in the coming weeks, but we do need more speakers always. So if you are interested in giving a talk, please just get in touch with me and we'll find a slot for you. So this week we're really pleased to be able to welcome Mario Motta, who is based at IBM Research in Silicon Valley. It's very early in the morning for him, so I hope you all appreciate him giving up his morning and getting up early for us. He is an expert in many sort of quantum many-body physics, in particular many electron systems. And today he's going to be telling us about determining eigenstates and thermal states on a quantum computer using quantum imaginary time evolution. So before I hand over, I'll just kind of recap the usual format, just in case we have any new viewers. So basically Mario is going to speak uninterrupted for sort of 45 minutes to an hour, however long he wants. And then at the end of the talk, we'll have moderated questions from the audience. So if you have any questions during the talk or after the talk, please just write them in the YouTube chat window and I'll relay them to Mario. Okay, so let's go to the science. So please go ahead, Mario.
Hello everyone. I should wish to begin by saying thanks to everyone, in particular Giacomo Guarnieri and Mark Mitchinson, for the possibility of giving this seminar, and to everyone for attending. So this seminar is about a suite of algorithms for the determination of eigen and thermal states on quantum computers. So let us maybe try to familiarize with these algorithms by saying a couple of words about the problem that they try to tackle, which is of course the many-body problem in quantum mechanics. And let me begin by reminding a fact that is very familiar to all of us, which is that the materials that we study in our research and that we ultimately care about for technological applications, they all comprise assemblies of many interacting electrons. So if we want to develop a theoretical understanding of this system that is sufficient to account for and even predict experimental observations, we need to be able to determine the quantum mechanical behavior of many particles that interact with each other, or in short, to simulate a many-body Hamiltonian. Now, simulating a many-body Hamiltonian is of course a very broad term and corresponds to a problem that is very multifaceted and complicated. It has nonetheless at least three important and very specific ramifications. One of them is the study of dynamics, so solving a time-dependent Schrödinger equation, which is important for a variety of excitation and transport properties. We have the problem of finding selected eigenstates of the Hamiltonian, in particular the ground state, which tells us about the physics or the chemistry of the system at zero temperature. And then we have the problem of sampling the equilibrium Gibbs distribution, the density operator e to the minus beta h for a system at equilibrium. In all these problems, a role of extreme importance is played by the Hamiltonian, which is of course given with some approximation. Even very simple systems, like spin systems, epitomized by the Heisenberg and the Ising Hamiltonians, though sacrificing some microscopic details, are able to give us an understanding, both theoretical and computational, of many important properties of materials, in particular the magnetic correlations and the magnetic phases. A higher level of realism is retrieved by lattice models of correlated electrons, where we bring back some important actual properties of electrons in materials, the fermionic indistinguishability and the interplay between kinetic energy and Coulomb repulsion among electrons, which is extremely important to understand phenomena like metal insulator transitions and certain phenomena related with high temperature superconductivity. These models are subject of very intense computational investigation these days. Even higher level of realism is obtained using first principle Hamiltonians. For example, a popular approximation in chemistry studies is the Born-Oppenheimer approximation, in which we decouple the motion of nuclei and electrons, so we can study molecules by fixing their nuclei at certain positions and accounting for the kinetic energy and the Coulomb interaction between the electrons and between the electrons and the nuclei. We typically fix a basis of certain orbitals for the electrons and have a second quantized representation of the Hamiltonian. Now, of course, 50 plus years of computational chemistry and physics have given rise to a considerable deal of approximate techniques for studying the Schrödinger equation in many body systems. They really are a large number. For example, there's density functional theory and mean field approximations that translate the effect of electron-electron interaction into the presence of a self-consistently determined external potential. Those of us who do chemical studies may have encountered Müller-Plesser perturbation theory, coupled cluster tensor networks, which are situations in which we formulate and optimize an ansatz for the ground state of a collection of electrons. And there are really a large number of other approaches. In particular, in recent times, some unconventional forms of computations, including quantum computing, have begun to emerge as alternative and complementary to what already exists. One thing that I would like to emphasize as a general view is that we shouldn't perceive all these techniques as completely distinct from each other, of course. Very frequently, ideas from a field can transport to another field or can be exchanged and borrowed. And in particular, in the development of novel computational schemes like quantum computing, it can be a fruitful area of research to try and explore what happens at the interface between seemingly distinct research fields. So since our topic is a particular form of quantum computing algorithm, let us spend a couple of words just to bring everybody on board in terms of what are quantum algorithms for quantum simulation. In what follows, I will refer to what is the dominant paradigm of quantum computing, which is the circuit paradigm. In the circuit paradigm, we have some computational units, which are called qubits and are, of course, two-level quantum systems. And we are given a register comprising many such qubits. A register can be initialized in a bit string state, which is a tensor product of zeros and ones corresponding to the ground or the excited state of our qubit. Such a register can then be manipulated by a unitary transformation and brought into a more complicated quantum state, which is a linear combination of these bit string states with, in general, arbitrary complex valued coefficients. Information is read out of a register of qubits by performing measurements, which of course destroy the quantum state that has to be regenerated for subsequent measurements and returns a binary string with a probability distribution, which of course is given by the square moduli of the components of the wave function. Sorry. Unitary transformations, of course, are at the core of quantum computations. And typically, these unitary transformations are represented as combinations of particular unitary transformations, the quantum gates, that act on small groups of qubits, typically one or two. Among them, we find very familiar gates like the Hadamard, the S gate, and the CNOT gate. So the general scheme of many quantum simulations comprises three phases: an initialization, in which often it is the case that we feed our quantum computer the input of a problem that we want to solve, then a subsequent manipulation through a set of unitary transformations, that implement some change in the state of the qubits, and then final measurements out of which we read the output, and we get the answer about the problem that we want to solve. And of course, such a scheme begs a question, which is whether and under which circumstances it is a good idea to use a quantum computer to solve a problem. This is a notion formalized by the concept of bounded error quantum polynomial time problems, or problems in the BQP complexity class. We have some problems whose size grows with some parameter, and as the size of the problem grows, the number of qubits and the number of gates and the number of measurements necessary to obtain a solution for the problem, roughly speaking, grows polynomially with the size of the problem itself. And so a natural question emerges, which is, where do quantum computers stand with respect to the problem of simulating a many-body system? And their role changes a little bit depending on the particular ramification of the problem that we consider. For a vast class of Hamiltonians, the problem of simulating the time-dependent Schrödinger equation is known to lie in the complexity class BQP. So it's a good application for a quantum computer, for which we know a considerable deal of algorithms. The situation is a little bit different for the eigenstate and the thermal state problems. Those are problems that belong to another complexity class called QMA, or quantum Merlin-Arthur, which means that in a general case, we are not able to guarantee that there will be a polynomially scaling quantum algorithm for the exact determination of these quantities. Instead, the algorithms that we have, including the quantum imaginary time evolution, have a heuristic character. I am by no means an expert of quantum computational complexity theory, but I should wish to recommend the book of Classical and Quantum Computation by Kitaev for a very accurate and a very accessible, nonetheless, introduction. Of course, so far we have been speaking about quantum computers that function ideally, as large as we please, with gates that are implemented exactly, and with perfectly ideal qubits. The quantum hardware technology is, of course, not that mature. The qubits that we do have these days are in relatively small registers. They comprise a few tens of qubits. They are noisy devices in which the gates are not implemented correctly, and there are decoherence phenomena limiting the half-life of the qubits. And they're also limited in connectivity, meaning that we cannot directly entangle any pair of qubits in our register. And so when designing and applying algorithms, we have to be mindful of these features. In particular, we have to focus on applications that fit the budget of the machines in terms of size, on circuits that are not too deep and too connected, and we have to deploy techniques for mitigating the errors that happen on the hardware. In short, we have to design our circuits in a way that is aware of the features of the hardware that we have these days. A very important class of algorithms that meet these requirements perfectly and are one of the workhorses of contemporary quantum computing are variational quantum algorithms, in which an initial wave function is manipulated through a parameterized quantum circuit U of theta. As the parameters in the circuit theta vary, we can explore, by application of this circuit, a manifold of many-body wave functions inside the Hilbert space of the system. Through measurements, we can compute properties of this wave function, for example, the expectation value of the energy. And if we have a technique for optimizing the value of a quantity that we care about as a function of these parameters, leveraging on the possibility of making measurements on the quantum computer, we can, for example, find the best approximation to the ground or to some excited states, in the case of the ground state, by minimizing the expectation value of the energy as a function of the parameters in our circuit. That is why variational quantum algorithms and many other algorithms have a hybrid quantum classical character. Starting from a given parameter configuration, we extract through measurement information out of the quantum computer about the value of the cost function and of its first, second derivatives, and then we use this information inside an algorithm of optimization implemented on a classical computer to update the values of the parameters. And we restart at each pull of the crank, improving the quality of our cost function until convergence as suitably defined. So it's in this situation that we have developed our suite of algorithms, starting with the quantum imaginary time evolution algorithm that we also call KITE. Of course, it's a natural question to wonder why developing an algorithm. It is fair to say that no algorithm, including KITE, comes free of any problems. There are, of course, algorithms that are able to give nearly exact estimates of eigenstates, for example, adiabatic state preparation followed by quantum phase estimation, but they are unsuited for contemporary quantum hardware where we don't have sophisticated forms of error correction, we don't have fault tolerance, and so they appear impractical in the near term. The hybrid quantum classical variational algorithms are excellent for the hardware that we have. Of course, they require you to formulate an ansatz which has to be carefully tailored, otherwise the algorithm will be fundamentally limited by the choice of the underlying ansatz. Moreover, they require us to perform optimization of many parameters in presence of noise. And so the question is whether we can devise other algorithms that maybe don't suffer from such forms of drawback. That's of course not to trash talk any of these algorithms. These algorithms are brilliant, but it is always a valuable idea to explore some alternatives. And in doing so, we have observed that many classical algorithms, especially quantum Monte Carlo algorithms, are based on the idea of imaginary time evolution. We start with the trial wave function, which is an ansatz for the ground state that is formally required just to be non-orthogonal to the ground state. If this non-orthogonality condition is met, when we apply the imaginary time evolution, the operator e to the minus beta h to the trial wave function, contributions to the trial wave function from the excited states fall off to zero exponentially with the rate controlled by the energy gap of the system. And in the limit of long imaginary time, we end up on the ground state. So imaginary time evolution can be used to access the ground and some selected excited states of a Hamiltonian. Imaginary time evolution is of course also the core of estimating thermal properties, and so it's very interesting to ask ourselves whether we can have quantum algorithms based on this idea. A glance of the equation on the left immediately shows us that there is a fundamental problem. Imaginary time evolution is not a physical operation, it's a mathematical abstraction. It's not unitary. In fact, it's even nonlinear. And so it is not a trivial problem to implement such an evolution on a quantum computer. Our approach to implementing imaginary time evolution is rooted on a physical idea, the physical idea of locality. For many Hamiltonians, and that includes the k-local Hamiltonians that we will see in a second, Hamiltonians that are linear combination of terms each acting on a group of k qubits. For many Hamiltonians and for many important wave functions, correlations decay rapidly in space. Let us take an example to better understand what I'm talking about. Let us consider a two-dimensional Ising model with transverse field, and let us compute the mutual information, which is a measure of entanglement, between two qubits I and j as a function of their distance, which is on the horizontal axis of this chart. And we computed a long imaginary time evolution starting from a factored state. That's the vertical axis, where we have the imaginary time, we start having qubit 1 or qubits entangled only at very, very short distance. As the imaginary time increases, correlations spread in the system, almost in a cone, until past a certain value, and for this specific system, we do observe a saturation of correlations. Qubits that have a distance higher than 7 in the particular topology of this example are not entangled with each other to a very good approximation. What does locality of correlation entail? In general, it entails that there is a simple structure in the ground state wave function, actually in the wave functions along imaginary time evolution for many models, that we can leverage in our algorithm development. If we are given a region of qubits A, that region of qubits will be appreciably entangled only with the neighborhood B of qubits close to that, and not with the rest of the system, what we call C in this chart, and we plot red, no matter how large that is. There's a warning sign here, so I'm not going to be making some precise mathematical statements now. It's just an impressionistic rendition that should help to digest some mathematical passages. Just for the purpose of roughly understanding, we can approximate or imagine that our system can be written as a tensor product of a piece for A and B, which are entangled with each other, and another piece for the environment. I repeat that this is not a precise mathematical statement. It just should help us a little bit understanding what happens, for example, when we try to evolve in imaginary time under a single k-local term of the Hamiltonian. Let us call it hk. And let us imagine that it acts on A. Starting from a wave function such that A is entangled with a neighborhood B, imaginary time evolution to leading order will change the entanglement pattern between A and B, but will not induce entanglement beyond the boundaries of B. And so the net result of this operation is to produce another wave function with the same structure of the initial wave function. It's just the wave function inside the group of qubits A and B that has changed. When we compare the initial and the final state, we immediately realize that there must be a unitary transformation acting on qubits in region A and in the neighborhood B that perfectly reproduces the action of the imaginary time evolution onto the current state. Now that we have an argument to find a unitary evolution, something that we can put on our quantum computer, the technical question becomes, how do we find this imaginary time, unitary evolution? Let us imagine to take a small step of imaginary time. Our transformation will not differ too much from the identity, so we can write our unitary transformation as the exponential of an anti-Hermitian operator and expand this anti-Hermitian operator on the basis of local qubit operators, for example, the Pauli operators, and linearize approximately the unitary transformation. With this approximation, which I repeat, requires us to take a small step of imaginary time evolution, we can determine the expansion coefficients and therefore the unitary by matching a couple of vectors. One vector is the vector delta of x that describes how the unitary transformation changes to leading order the state of the system. The other one is this delta 0, which describes to leading order how imaginary time evolution under a single k-local term changes the state of the system. And what we want to minimize is essentially their distance, so that the two vectors match each other and the unitary to leading order reproduces the action of imaginary time evolution. Now, this is one of the few dense slides, but let's go through it gradually. If we look at the vector delta 0, we may scratch our head a little bit, because we have an imaginary time evolution operation inside it. And we are setting up all this cancan because we are not able to implement in a simple way imaginary time evolution on a quantum computer. So we may have the feeling that there is some conceptual problem here. However, we are performing imaginary time evolution for a short step under a k-local observable by construction. What does that mean? It means that since our operator hk acts on a little group of qubits, we can compute at a cost that doesn't scale exponentially all its powers. And so we can really represent the vector delta zero in terms of a linear combination of many terms involving the powers of hk. The simplest approximation in that spirit, which is justified by the smallness of the time step, is to just linearize the vector delta zero. So now we have a known vector delta zero and another vector that depends linearly on the coefficients x mu. That means that when we try to write down the squared of the distance between the two vectors, we end up with a second degree polynomial in the variables x, a parabola essentially. And we all know how to find the minimum of a parabola. We just have to solve a linear system in the unknowns x, where both the matrix involved in the linear system and the vector involved in the linear system can be determined on the quantum hardware, given a wave function, by measuring anti-commutators between Pauli operators, local Pauli operators, and their commutator with the various terms in the Hamiltonian. And so that gives us the flowchart of the kite algorithm. We take the imaginary time amount for which we want to evolve and chop it into many small pieces, or steps or slices. For every step, we perform a Trotter approximation of the imaginary time evolution operator, so we are left with the task of evolving under single k-local terms individually. For every k-local term, we select a neighborhood of the domain, the group of qubits where the local term acts. We perform suitable measurements and construct our kite linear system. We solve this linear system, and we construct the unitary transformation U that implements imaginary time evolution for a small step under a single term. We attach this unitary to a starting quantum circuit, and we augmented it progressively until we have projected in imaginary time. Because this construction may appear a little bit remote, let us just focus for a second on a small example so we can turn all these operations into something simple and concrete. Let us consider a two-sidizing Hamiltonian. We have our z operators and then a coupling term with x operators. In this simple two-qubit system, we know that the ground state is a linear combination of 0, 0 and 1, 1 with coefficients that correspond to the sine and the cosine of an angle. And so given an initial state, which is, for example, 0, 0, we can reach the ground state by only applying the exponential of x, y. That's, of course, specific of this particular system. And it's a simplification that arises from its small size and from its symmetries. So we can think about a reduced kite algorithm in which we just need to consider one operator in our pool of local Pauli operators. And of course, there's not really a linear system to solve. The anti-commutator of a Pauli with itself gives us 2. No matter the wave function, we can compute the commutator between the Pauli and the Hamiltonian. That's the operator that we see on the second equation. And given a circuit, for example, the initial one, we can evaluate this expectation value, construct our B, and determine the angle theta that corresponds to a small step of evolution in imaginary time under the Ising Hamiltonian. What you see on the bottom right is the quantum circuit to implement just one of these steps. We move in the eigenbasis of xy, and then we apply a controlled RZ rotation, and then we get back to the original basis. And that's a step. Once we have carried out a step, we repeat the measurement of S and of B on the updated circuit. We find yet another value of the angle, and we go on until convergence. So now that we are a little bit familiar, let us try to look at the algorithm at work. Let us consider a simple example, a system of 10 qubits with a short-range Heisenberg Hamiltonian in one dimension. On the left, we have a series of colorful curves that are kite simulations with unitaries acting on 2, 4, 6, 8 qubits, so larger and larger domains. And what we see is that, unsurprisingly, the quality of the energy increases when the domain of the unitaries increases from 2 to 4 to 6 and to 8. One thing that is important to observe is that because of the underlying approximations, the kite energy is not guaranteed to be monotonic in imaginary time, especially for small values of the size of the domain. It's not just the energy that improves in quality, it's the overall wave function. Indeed, on the right, what we see is the fidelity between the wave function output by kite and the ground state wave function of the system. And the fidelity, of course, increases monotonically with the size of the domains of the unitary transformations defined in our quantum circuit. So indeed, any property that we can harvest out of the kite wave function will be systematically closer to its ground state expectation value when we increase the size of the domains of the local unitaries. What we saw in the previous slide is a demonstration of the algorithm on a classical simulator, a normal computer, just to assess its performance and make sure it's bug-free. But that's an algorithm that we have been able to implement and run on real hardware. In particular, here we see a simulation of a full-site Heisenberg model carried out on some real hardware, the hardware called Aspen by the Rigetti company. What we care about is, of course, for now, the blue curve, where as a function of imaginary time, the energy decreases and then stabilizes around the ground state expectation value. Now, at this point, we have realized that the bottleneck of kite is associated with the local measurements. In order to construct our circuit, we basically have to perform a partial tomography on the system. And that's an operation that indeed, in full generality, scales exponentially with the size of our neighborhoods, our uppercase D parameter. And so we may have the feeling that kite is a very expensive methodology. It certainly can become such if we use very large neighborhoods. But for the problems that we can study on contemporary hardware without any simplifications, it turns out that the budget of kite is comparable with the budget of existing simulations. What we see on the right plot is the total number of measurements of Pauli operators that we need to converge the ground state energy of a Heisenberg Hamiltonian within 1% using kite, that's the orange column, and using a hardware efficient implementation of the variational quantum eigensolver, or VQE, which is the blue columns. And that's a popular, excellent algorithm for a lot of applications. We see that the two budgets compare favorably with each other, which means that kite is an affordable methodology. Imaginary time evolution is not just a tool that we can use to get to the ground state of a system. It can also be used as a subroutine inside other algorithms. And those are the algorithms that we will now discuss in the final part of the talk. One is the quantum Lanczos and the other one the quantum Metz. Let us start with the quantum Lanczos, which is of course a quantum version of the Lanczos diagonalization algorithm. As we project an initial wave function phi in imaginary time, we visit several vectors inside a Hilbert space. And if we had all these vectors available for us, they would of course form the basis of a subspace of the Hilbert space. And in such a subspace, the best approximation for the ground and selected excited states of the Hamiltonian is of course a linear combination of the basis functions with coefficients that are determined by solving a generalized eigenvalue equation. This generalized eigenvalue equation will involve a Hamiltonian matrix, the matrix elements of the Hamiltonian between the basis functions chi-r, and an overlap matrix, the overlaps between the basis functions themselves. In the bottom, we see an example of what these Hamiltonian and overlap matrices look like for a simple chemical system, a water molecule at the equilibrium geometry with a minimal STO6G basis. The diagonal of the Hamiltonian matrix will contain the kite estimate of the energy, the expectation value of the Hamiltonian over wave functions projected for increasingly high imaginary time. If we combine our projections in imaginary time of the initial wave function, which here is the Hartree-Fock state of the molecule, into a linear combination, we can obtain a much better and much quicker converging to the ground state estimate for the energy through essentially a Lanczos algorithm. And the main question underlying quantum Lanczos, but also underlying every form of quantum diagonalization algorithms, we have a few citations here. That's really a beautiful and very active field of research in quantum simulation, is how to extract the Hamiltonian and the overlap matrices out of a quantum computer. That's in general not an easy task. However, when we are studying exact imaginary time evolution, an important simplification occurs. We are constructing our active space, our basis for the Lanczos subspace, by applying some Hermitian operators, e to the minus delta tau h raised to some power r or s, which commute with the Hamiltonian. And so then what we can do is we can redistribute imaginary time evolution between the bra and the cat in such a way as to symmetrize it, so that our matrix elements of the Hamiltonian, even those that are off diagonal, can be reduced to diagonal expectation values in which the bra and the cat are identical to each other, which is how we carry out, of course, standard measurements on quantum hardware. The ability to write down the matrix elements of the Hamiltonian as diagonal expectation values requires us to be able to compute the norm of a wave function projected in imaginary time. That's of course because of some multiply and divide tricks. These norms, though not directly accessible, can be computed by a recursive formula. Essentially, whenever we try to augment the imaginary time projection by a step, our squared norm follows a telescopic product formula. The new norm is equal to the old norm times the expectation value of e to the minus delta tau h over the current wave function, which of course we can linearize or approximate to second order because we are taking small steps. What we see here is a comparison between some empty marker curves, which are kite estimates of the energy, with unitaries acting on 2 qubits and 4 qubits on the left and on the right respectively for a 20-qubit Heisenberg model. There are also points with a field marker. Those are the quantum Lanczos estimates. And we see that for all values of the imaginary time, quantum Lanczos gives us an estimate, unsurprisingly, of the ground state energy, which is lower than what kite gives us. We may be surprised by seeing that the curve with 2 local unitaries is non-monotonic in the energy. However, it can be accounted for by observing that our quantum imaginary time evolution is approximate because of the small size of the unitary transformations, and therefore it is not guaranteed that the identities presented in the previous slide will hold perfectly. That is responsible for some approximations. In addition to that, we have to be mindful that since we are evolving our wave functions along imaginary time evolution, so we are implementing a continuous transformations, the overlap between wave functions evolved for a small number of steps is quite high, quite close to 1. And so then to avoid ill-conditioned linear systems, we have to select some vectors out of our pool and some matrix elements for both the Hamiltonian and the overlap, so that we obtain a numerically stable solution. Nevertheless, quantum Lanczos always helps us improving the energy of the ground state over the basic kite formalism. Another application, even more important, is the evaluation of thermal averages, which we can carry out whenever we have a subroutine that implements imaginary time evolution. How can we do that? Let us start with the definition of a thermal average. Oh, sorry, there should have been a missing trace symbol in the denominator. We have a trace at the numerator and a trace of the denominator. If we split e to the minus beta h into e to the minus beta over 2h, repeated twice, and we use the cyclicity of trace to move one of the propagators at the bra, and then we insert a completeness, for example, on the basis of binary strings, we can represent the thermal expectation value of an observable as essentially a fraction with a numerator and a denominator that involve squared norms and expectation values of the observable of interest over wave functions projected in imaginary time. Because we want to deal with normalized wave functions, that's of course what our quantum algorithm outputs for us, we multiply and divide times the squared norms, the same quantities we computed in quantum Lanczos, to obtain the final expression that we have in the first equality of the second line. Essentially, we have that our thermal average is an expectation value, a linear combination, of expectation values of the observable of interest over normalized wave functions projected in imaginary time and weighted by a probability distribution. So the task of evaluating a thermal average is reduced to the task of evaluating an expectation value, which in turn, of course, requires sampling the probability distribution in a way that is scalable and efficient. That's, of course, a problem that has already been studied in simulations on classical computers. There's a very nice paper by Stephen White which delineates the METS, or minimally entangled typical thermal state algorithm, which is a sampling procedure essentially for this probability distribution. We start from a random binary string I. We project this string in imaginary time using, for example, kite as a subroutine. Once we have carried out the projection, we can evaluate every property of interest by repeated measurement. Then, of course, we need to choose yet another binary string. And how can we do that? We can measure the imaginary time evolved wave function phi. This will leave us with a random binary string by wave function collapse. And from this new binary string, we can restart the procedure. It was proved in the original METS paper that this procedure is conductive towards an unbiased sampling of the probability distribution. And so we have been able to use it to evaluate thermal expectation values of the energy for Heisenberg Hamiltonians of a small number of sites, once again changing the size of the domain D over which local unitary transformations are applied. That's a 6-site Heisenberg model on both quantum emulators as well as on quantum hardware. So just to summarize, we have prepared a suite of algorithms to implement imaginary time evolution on digital quantum computers. This is an algorithm that, unlike variational algorithms, doesn't require you to formulate a variational ansatz and doesn't require you to carry out nonlinear parameter optimizations, just to solve linear systems, which, if you can do it reliably, because the noise is not too intense, is guaranteed to give you convergence to the global minimum of the energy. Of course, the algorithm comes with approximations. We make a Trotter decomposition of the imaginary time evolution, and so we have a finite time step error. We unavoidably apply unitary transformations that act on a small finite number of qubits in our system. That induces, of course, another approximation that we have seen and appreciated in the slides. Nonetheless, we can obtain systematically better estimates of all the quantities involved by increasing the value of this size of neighborhoods. Of course, and especially on a noisy hardware, we're not able to project for an indefinite amount of imaginary time. We may have to stop at a finite value of the imaginary time. And that's sufficient to give us a variational answer for the ground state of the system. In all these aspects, kite is systematically improvable by increasing the number of qubits upon which unitaries apply and the imaginary time of projection. Of course, when we are dealing with a noisy quantum hardware, we can always reduce these two parameters to what is the budget of the machine and carry out a valid simulation that gives us a variational, possibly not accurate, of course, answer. There is a computational cost connected with kite, which is concentrated for k-local Hamiltonians in an exponential dependence on the number of Pauli operators, on the size d of the domains of the unitaries through the number of Pauli operators. But it remains polynomial in the system size and doesn't increase exponentially with the imaginary time evolution. Of course, one can introduce many different approximations. One can consider Pauli operators where the weight is capped, or that are highly structured based on some initial scheming. And so at the cost of sacrificing exactness, this computational cost can be brought down. Kite has two applications. One is the quantum Lanczos to refine the estimates of ground state energies and wave function, but also to access selected excited states. The other one is QMETS, which gives us access to thermal expectation values. And that's of course a work that we published. There's much more information in the original paper and in its supplemental information. That's a work that was carried out by many different persons. They are all outstanding scientists and wonderful people that I deeply carry in my heart. Thank you to all of them, Chong, Adrian, Matthew, Erika, Austin, Fernando, and especially Garnet, a fantastic supervisor. Thanks everyone for your attention, and I should be delighted to try and answer any questions you might have.
Thank you very much, Mario. Really beautifully clear talk. Thank you so much. And we have lots of questions. Okay, so let me just go through them kind of in order. Okay, so the first question was kind of a general question from Ish Gupta, who asked, "What is imaginary about imaginary time evolution? What does this mean physically? And how is this different from evolution done in variational quantum algorithms?"
Okay, so what is imaginary about imaginary time evolution is the fact that you can think about your real time evolution operator, which is of course e to the minus I th. If you were to replace the time variable, which is of course a real valued quantity, with a purely imaginary quantity, let us say minus I beta, then e to the minus I beta h would turn into e to the minus beta h. In this sense, it's taking a real valued variable, which is, of course, the time, and turning it into a complex, actually a purely imaginary variable, that turns the real time evolution operator into the imaginary time evolution operator. How is it different from the works by McArdle and Benjamin, where variational imaginary time evolution is carried out, is an absolutely excellent question. There is a difference. The difference is that in their algorithms, we are in a variational framework. So essentially, we are applying a parameterized quantum circuit to an initial wave function. And what we do, well, what they do, sorry, is to identify the optimal values of the parameters by setting up a differential equation for those parameters, which is derived by reducing the imaginary time evolution inside the variational manifold. In other words, let us come back to the Ising model for a second. You could also see this example as a framework where you can implement variational imaginary time evolution. Let us say you start from 0, 0, you apply the particular unitary that you see here, okay? You have the exponential of a Pauli operator with an angle. That's your circuit down there. Now the angle is a parameter, okay? And how do I find the optimal value of that parameter? Maybe I minimize the energy, as I would do with SPSA or BFGS, any optimizer. Maybe I write a differential equation for this parameter. So I call it theta of beta, and I write down a differential equation that imposes that the flow of this curve of wave functions inside our manifold best approximates the imaginary time evolution inside the manifold to which we are given access. So I would call it, and hopefully that's not an inaccurate description, an imaginary time-based technique for parameter optimization in variational algorithms. And that's very fascinating because you can implement that also for real-time evolution. I think Sam and Simon have written papers about that. And it's reminiscent of a very old, very nice technique that exists in Variational, Monte Carlo. I think the first person to implement it was Sandro Sorella, but there's also a very nice paper by Toulouse and Umrigar, which is called the linear method. Essentially, you set up a differential equation for your parameters based on imaginary time evolution projected on your variational manifold. That's our difference, essentially.
Okay, thanks very much. So lots more questions to go, so let me just go through them. So the next question is from Giacomo Guarnieri, who says, "Hi Mario, thanks for the great talk. Concerning the kite algorithm, what are the consequences of eventual external noise on the solution of the linear system?"
Yes, that's a very, very, very important question. Because in general, you will be measuring a matrix, matrix element by matrix element, with these anti-commutators, and then a vector. So essentially you have both a matrix and a vector where every entry has a variance. And of course, I will not try to enter into random matrix theory or anything similar, but let us imagine that your matrices have a certain size in their elements, let's say order unity, and your error bars have size, let us say 10 to the minus k. Of course, when you have very small error bars, very small relatively to the magnitude of the matrix elements, the solution that you get out of the noisy linear system, which is of course a random variable, x becomes a random variable, has very little bias and very little fluctuations. On the other hand, when your error bars begin to compete in magnitude with the matrix elements, that's where essentially you can have large biases on the value of x, as well as large statistical fluctuations. So in that situation, the noise changes the properties of your matrices and your vectors and is capable of changing the solution of the linear system. That's true, by the way, for every quantum algorithm that tries to address the solution of a linear system or an eigenvalue equation based on noisy matrices and vectors. In that case, to avoid your solution to behave in a pathological way, you need regularizers. So for example, to make sure that the overlap matrix S remains a positive definite, you may have to add to it, let us say, gamma plus the identity. In general, as long as you can, as much as you can, you should definitely try to reduce the magnitude of the error bars by accumulating statistical samples. What is more subtle is the effect of biases, right? Because you don't just have statistical finite statistical sample problems connected with the measurements of matrices and vectors. You also have biases from noise in perfect gate implementation. And in such a case, the effect is a little bit more difficult, more subtle to address. That's, I think, an effort that deserves a lot of attention. One can carry out systematic simulations on both hardware as well as on classical emulators, not just for kite, but for a lot of different algorithms, to empirically assess what is the impact of both. I would say that, of course, when the biases and the statistical fluctuations become overwhelming, then the solution is not guaranteed to be reliable anymore. You can stabilize it, yes, with a regularizer. To reduce the size of the error bars, you should definitely gather statistical samples. To reduce the biases, you can use error mitigation techniques. For example, there are readout error mitigation techniques, where essentially you take a bunch of circuits, maybe comprising Clifford gates, so that you can efficiently evaluate their output probability distributions on a classical computer. You measure these probability distributions on the hardware and you get something different because of noise. What you can do is you can set up a fitting function that describes how the ideal probability distribution turns into the noisy probability distribution. And when you run an arbitrary circuit, you can apply the inverse of that corrective map to the noisy probability distribution. And so that should take care to lead in order of the readout errors. There are also gate error mitigation techniques. In particular, the Richardson extrapolation is one that has been developed within IBM, and it's a terrific tool, very helpful for deep circuits. So there are techniques also for bias reduction, and I think it's a very valuable effort in general to accumulate as much knowledge as you can on this very nice applied math problem.
Okay, thanks very much. Super detailed answer there. So we do have like 5 or 6 more questions, so I'll just go through them. So the next question is from Andre Timpanaro, who asks, how does the quantum thermal average compare with usual quantum Monte Carlo algorithms that normally simulate imaginary time evolution in classical hardware? And he has another kind of related question that I'll just throw in there, which is the quantum thermal average susceptible to sign problems? okay, which is of course also related to Monte Carlo, right?
Yes, that's a very good question. We have not carried out extensive comparisons against classical techniques for large systems for two reasons. The first one is that our classical simulators under the hood use a full CI wave function, so we are limited in scaling. And the second one is that the hardware itself, which is where you should be running these algorithms, is in this NISQ phase, where essentially the size of the demonstrations has its limitations. So I think that it is fair to say that we don't have any empirical data about such a comparison. What I can say is that if we look at the METS estimator, at our representation of the thermal average as the sampling of a probability distribution, we do not have any form of 0 over 0 or infinite over infinite or infinite minus infinite indeterminate form, which is the way normally the sign problem manifests. So if this was a system of fermions and we were implementing a path integral Monte Carlo, we would have an imaginary time evolution which is broken down into many small steps. For every step, we insert a resolution of the identity on real space configurations and spin configurations. And when we evaluate the trace at both the numerator and the denominator, we end up having a sum of the permutations. So in both the numerator and the denominator, we have positive and negative signs. Each goes to infinity in magnitude, and it's only through a cancellation of contributions that you obtain the physical properties. So you have a very large signal to noise ratio, essentially because you cannot guarantee that you have positive quantities everywhere. You can, of course, constrain the sampling. That's done all the time in diffusion Monte Carlo, in auxiliary fields, quantum Monte Carlo. And so then you introduce biases by getting rid of the sign problem. When it comes to METS, I do not see any signatures of sign problem. The only potential problem is with the structure of the probability distribution. When you go to a large system, if it happens that the probability distribution is very peaked, it may be difficult to practically sample it. You may need a considerable number of samples to make sure that you ergodically explore all your sample space. I don't think that's an entirely satisfactory answer. It just summarizes what is my knowledge on the topic. I do not see any signature of sign problem, but I cannot rule out that the sampling will be difficult for a large system. Of course, I would say that the real practical problem, actually, in implementing kite and METS lies in having a good approximation for the imaginary time evolution in these states VI. That's where I think the real difficulty may lie. And that's system dependent. The moment you go in a system where the correlation length diverges, that's where essentially your approximations based on locality break down. And so that's where kite may not be able to provide a satisfactory estimate of the thermal problem.
Okay, thanks very much. Let's move to the next question. So Pablo Poggi asks, "Hi, I am curious about the experimental implementation on Righetti's Aspen.
Mhm.
Do these results correspond to simulations using the full qubit layout? 16, I think," he says.
Oh, no, 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 no. We didn't use the full hardware. We essentially used a few qubits out of the full hardware. And we have details of that in our supplemental information. We used also qubit reduction techniques, what goes by the name of qubit tapering off, essentially. So in our spin systems, we do have some symmetries. And so what we can do is we can apply a preliminary unitary transformation so that one or more qubits store the irreducible representation of the symmetry group where the initial wave function lies and where imaginary time evolution is limited. So for example, let us assume that, like in the harmonic oscillator, you have even and odd wave functions. If you start your imaginary time evolution with an even wave function, because the harmonic oscillator Hamiltonian is parity preserving, you will always remain in an even wave function. So if you apply a unitary transformation and make sure that one of the qubits stores the parity, then you know that that qubit is supposed never to evolve during the simulation, and so then you can freeze it. All of that is to say that we used 1 to 4 qubits in our simulations. That's not really like using the full Aspen.
Okay, thanks very much. So we have kind of the same question, I think, from two different people, from Kenneth Young and from Gavin Jones, who are basically asking, is it possible to obtain excited states with this algorithm, and what are the limits on the excited states that can be computed?
That's a very, very good question. It is possible in two ways. And there's a paper that was published this year on MPJ quantum information by a group of researchers from Oak Ridge. Essentially, there are some excited states that you can get very easily and naturally. And those are the lowest energy states in a sector of the Hilbert space that has a quantum number different from the ground state. So for example, we spoke about the harmonic oscillator a minute ago. If you start from an even wave function and project it in imaginary time, you're gonna get the ground state in the subspace of even wave functions of the harmonic oscillator, which is the ground state of the system at all, of the system period. If you start from an odd wave function and your imaginary time evolution doesn't allow for leakage from the odd to the even subspace, then you're going to get the lowest energy odd wave function, which is of course that first degree Hermite polynomial times the Gaussian. And so those are excited states that you can get very easily and naturally with kite. So you can get, for example, ionization potentials, electron affinities. You're going to have to pay attention to the diffuse orbitals if you try to do so. In general, quantum Lanczos can give you access to excited states that have the same quantum number of the ground state. So there are other excited states that you can get through quantum Lanczos. Of course, if you want to get a good number of states, you need a good number of basis functions. And in general, extracting accurate excited states is trickier than it is to extract ground states. But that's possible nonetheless. You can do projection in imaginary time in a different sector of the Hilbert space and use quantum Lanczos on top of both. So for example, also singlet, triplet gap, you can get like that. If you can make sure that you start from an eigenfunction of spin squared with eigenvalue 0 or 1, you will remain in that subspace across imaginary time evolution. So you do two calculations, get an energy difference, and here's your gap.
Thank you. Okay, so next question from Luke Rowantree, who asks, is the quantum Lanczos algorithm tied to solving a Hermitian eigen problem in the same way as the classical analog is, or could it be applied to a more general eigen problem like the classical Arnoldi method?
Well, our quantum Lanczos is formulated for Hermitian matrices. I cannot think about non-Hermitian generalization, but I can't rule out that those could exist. That's research, I think. Yes, your matrices come out naturally as Hermitian.
Okay. Maybe something that you guys can discuss over email at a future point. It sounds like an interesting problem. So let's move on to the next question from John Gould, who asks, is there any known algorithm in quantum computing to rescale the Hamiltonian spectrum efficiently so that you can shift excited states to lower energy, which is what we often do in numerics to do partial diagonalization using Lanczos?
Maybe. I can't say that I'm aware of those. That may just be out of my ignorance.
Okay, fair enough.
That's a very good question.
Maybe.
So the easiest thing that I can think about, I don't know if that's useful at all. If one want, and that also ties with the excited states question before. In principle, if you are willing to pay the price of implementing imaginary time evolution, not under h, but under h minus omega squared, the ground state of h minus omega, there's round bracket h minus omega round bracket squared, that would be the eigenstate of h with energy closest to omega. So I think there's quite a bit that one can explore there, even on the basis of such a simple observation.
Okay, thanks. So then I think in the interest of time, let's make this the last question. Interesting question from Juan Jose Mendoza Arenas, who asks, thanks a lot for the nice talk. Is there a prospect to calculate steady states of open systems with this technique? For example, evolution under a Lindblad master equation?
Oh, that's a terrific question. Well, that requires a considerable deal of thought. So, in principle, the kite procedure is not limited to e to the minus beta h. You may have any operation. Okay, let us say, for example, you want to apply just to fix ideas. That's not a Lindbladian, but that's just an example. Let's say you have a wave function and you want to apply, you have a spin system, an operator that raises the spin, right? The S plus, the one that goes from 0 to 1 to a single spin. Now that's of course non-Hermitian, non-linear, blah, blah. And so then if spin that you're trying to raise is entangled to a neighborhood, what you can do is you can represent approximately the action of this nonlinear operator with a local unitary. So in other words, you can recycle the kite procedure to other form of processes, not necessarily just e to the minus beta h. And so that lends support to the view that one may be able to implement more sophisticated forms of evolution. I have never been thinking about the specific difficulties that simulating the Lindblad equation entails. Certainly one to think carefully about is that one is going to have to deal with states that are not pure. So it's not a wave function to wave function transformation. So maybe the right generalization there is to use a kite procedure to produce a Krauss map, a Krauss representation of a CPTP map by sort of fitting the various Krauss terms. That's a little bit of a smoky answer. Truth is, I never really thought about that. But it's at least encouraging that you can generalize the kite procedure to something that is not e to the minus beta h.
Okay, thanks very much. Yeah, so I think I've had lots of questions, so it's probably a good time to wrap up. So I think I managed to ask a question from everyone who wanted to ask one. If anyone has any further questions for Mario, I'm sure you can just get in touch with him directly and continue the discussions and so on. So thanks very much, everyone, for tuning in again and for your really nice participation. And especially thanks to you, Mario, for such a nice and clear talk.
Thanks, everyone. In particular, thank you to you and to Giacomo. That was a great opportunity. Thank you. And I remain available for any curiosities.